known person here in Brazil at IMPA, especially. And he's going to speak on new type of thing he's considering nowadays, which is, I think, learning theory, how to learn things, how to do those things. He wants to mathematize that somehow. Conceptual thing, you see, more or less, I guess, in the spirit of what von Neumann and Hermann Wright did for quantum mechanics, some kind of, in this direction at least. And so, and today he's going to speak on evolution of language. Is that correct?
Yeah. Thanks, Mauricio. Let me express my congratulations to IMPA and also to its director, Jaco, for his inspiration and leadership for IMPA and for mathematics. And for myself, I certainly have it's been a great treasure in my many years of association with both IMPA and Jaco. Okay, so I'd like to talk today about evolution of languages, and to paraphrase the main result, one could say that what I would like to do is to give a mathematical proof that languages can exist. Okay, well, we'll see. So, you know, the basic the underpinnings of the mathematics of languages and the description I give today have to do with with learning theory. Learning theory is a theory of learning by induction, mainly by learning by example, and that's what I will be giving a model of languages, which is ultimately based on individual behavior of learning a language or modifying a language through conversation being the examples. Okay, so let me start by saying a little bit about learning theory. I'm going to be speaking on different levels. There's a superficial level of learning theory which gives some of the main ideas based on fitness, which I can describe more easily, so I'll do that first, and then try to replace that with some modifications by learning with individual behavior instead of fitness, and that gives a much more deep and satisfactory account of learning a language, and convergence to a common language, conditions for convergence to a common language. And that's what I mean when I say it's a mathematical theorem that languages can exist, is a convergence to a stable common language. Language equilibrium, so to speak, under fairly reasonable linguistic hypotheses. Okay, so learning theory means learning by examples. For example, Newton coming across with some law of physics by watching apples fall. That's an example of a physicist learning a physical law, and a more precise version of the same is in a laboratory. We have a given x and y axes, and examples then are produced in the laboratory, so we get data points. Here we'll have x1, y1. Another point, x2, y2, produced, for example, by a laboratory experiment. Another one, and so on. And from this data, the physicist would like to deduce some physical law which explains this data. Here we have xi, yi. So the idea is to fit a function to explain this data. So here in this case, it might come something like that. So this would be an expression of a function f from x to y, which can explain the data. This is a crude and simple picture of a physicist learning a physical law from data in the laboratory. Now, a couple of things that are involved here have to do with the candidates for f to begin with. Unless one makes some hypotheses about the space of f, one cannot get very far here. So one might take f to belong to a certain family of functions. It could be of the type f of x equals constant xi, I going from 0 to d, dth degree polynomials. And then if we fix d, this would fix the family. And one could search for hypothesis to explain the data within this family fd. So one usually has to have some kind of framework in which to learn. And the framework would be this function space for which one searches the best possible hypothesis to explain the data. So this is a kind of a universal phenomena, or we might call it a phenomena of learning. Okay, another example. So in this case, we're thinking of functions then from a space x to a space y. Now, the example that we'll be talking about in this talk, these are languages. So I want to think of a language as a map from a space x to a space y. X in learning theory, and let me just give a reference. The learning theory is exposited, or our work in learning theory is in a paper with Felipe Kuker. And it's published just very recently in the AMS, Bulletin of the American Math Society, pages 1 to 50. And this is January of this year. There you'll see mathematical foundations of learning theory in the rigorous systematic account, which we're using in this language talk. So we use one of the main theorems here as the main theorem in the talk. And we've been joined by Zhou, Dingshuan Zhou, for this work, which is unwritten. This is only partially written on the evolution of languages. Okay, so we want to now think of a language as a map from a space of meanings, x, to a space of signals or words, y. Okay, so x then will be interpreted as a space of meanings. And y, this would be a Euclidean space. Well, linguists would say signals. You can think of that as words, phrases, and so on. So this we would take to be a compact subset of R and say. So X, the space of meanings I would take to be a compact space. And let me give a couple examples of languages. So then a language is a map from a space of meanings to a space of words or signals. Example, here might be a dog. I'm not exactly an artist. So this is the meaning of a dog, or I could just say dog. Goes into a word, dog. Very simple example of a language. 1 point in each space. Now if you take a house, so it's a question, can we express languages in this way? And certainly linguists have not usually done that. The linguistic theory is done pretty much in the formal grammar of Chomsky, where everything is discrete. And I think by now there's almost a little bit of a revolt, an anti-Chomskyan revolt in linguistic circles, and I'm certainly consider myself part of that revolt, and that we deal with meanings. Chomsky does not does not deal with meanings. It's all syntax. And so one has to think about it. Even for linguists, this is very unusual to think of a language as a map in this sort of setup of continuity. But let me give an example of a house. You can think of this as a meaning. And a house, how can a house be in a space X? Well, one simple answer to that is just take a photograph of the house. Photograph of the house is a function. You can think of that as a function, gray-white function, on a rectangle. And that can certainly be put into a space X with very little mathematical work, even a compact space. So you can think of just naively saying houses are represented in X as a photograph, or if you want, you could say it much more economically by an artist like Picasso, who can just in a few lines characterize a house. And our house would be a particular photograph, which people could recognize. So our house would be a particular point in the space X of houses represented by photographs. And that's an example. Another example of a language, let me give a little more technical example. Let's consider space of meanings, gray meanings, white to black, on the scale from 0 to 1. So these are meanings, all shades of gray, going from pure white to pure black. Okay, and here's our space Y. So this is X. And over here, let's put the word white. And over here, the word black. So a language of a very young person might consist just of two words, white and black. So more or less everything over here would be go into the symbol white, everything over here into the word black. So it would be a discontinuous map for a very, very immature speaker. Just two words. Then a more sophisticated speaker, we could put in here the word gray. Now, what is a language of a sophisticated speaker? Well, everything very close to white, a sophisticated speaker would use the word white for. So all this would get mapped into the single point. This interval about meaning white would go into a single word black. Single word white. And the same over here. So all these meanings will go into this point. And same over here. In the middle, some interval about here, our idealized mature speaker would take into the word gray. Okay? That still leaves some points here. On these points, the same speaker, by what linguists would call ambiguity in speech, might use sometimes the word white and sometimes the word gray, or pointed in here. So this, in our language, example of a language, would get mapped continuously into here, into this interval between white and gray, with the interpretation that the likelihood of using white would be somehow the distance along this interval over here to white. And so this would be stretched out approximately linearly between this little interval here and this. And the same over here. This way one gets a continuous map. As an example of a language from 0, 1 to this segment in word space. So this is an example of a more sophisticated example of a language. And now one can start building up. And it's something that certainly I'm not doing systematically, take complicated languages and try to understand them this way, but just give some examples why it makes a lot of sense and one gets reasonable interpretations of these maps, spaces x to y, as a language. And one has many, well, I emphasize there are many interpretations just for a single map. You can make many interpretations. And the important thing is to have at least a realistic, reasonable interpretation. That's what I'd like to do, say that there exists a reasonable interpretation of things I do. Okay, anyway, be sure to stop me if I'm saying things less than understandable or you have objections or whatever. Okay. So this is a language. And now it's important to add one other ingredient to this space x. I want to put a probability measure on x, row x. And this indicates, in the environment of which we speak, the frequency of a certain meaning. For example, here we might have tigers and dogs, but in a big city, the frequency of a dog would be much, much higher than that of a dog. And this probabilistic measure on x represents that frequency, frequency of meanings. The meanings have something in existence apart from a language in this way of thinking that I'm speaking of. Okay. So now I want to talk about a linguistic community. So I want to talk about a space, F, say, of languages. This is some space of languages of the community. Or even more generally, what I'll do is to talk about the distance of two languages with an interpretation of ability to communicate of agents using the respective languages. So I'll talk about the distance of two languages, distance Fg equal the integral, and now I integrate over the probability measure on x, f of x minus g of x. I take the norm on y, it's a Euclidean space, dx. Squared, squared. And so the distance is small. One interprets that as the ability of speakers using F and G to communicate. For example, if the distance is 0, these are the same, so you have the maximal communication between F and G, but linguists using F and G. Language speakers, linguistic agents. Okay, so now let's talk about this linguistic community. Of agents. So we have agents, 1 up to, say, k. K agents. Let me just make a little digression. There has been an awful lot of work in the last years on evolution of languages. There was a big conference at Harvard 3 months ago on the subject of evolution of language. 400 people were there. Most of that work is either work in the field or maybe numerical simulations. And especially the numerical simulations of some models have been helpful to me in this. And there's one other model by Nowak at the Institute for Advanced Study, Martin Nowak, and Partha Niyogi at the University of Chicago. They have a model on the evolution of languages, which is actually quite different from this one. I think it starts with the Chomsky framework, although eventually they say it can incorporate meanings, and I'm sure it can. But they need an infinite population for their model to work. And they take into account more fitness in a more serious way than I do, and very little individual behavior. And there are some very major differences. But there is another model, mathematical model on the evolution of languages with associated especially to the names of Martin Nowak and Partha Niyogi. Okay, so we have these agents, finite number of agents in our situation. And we have a state of this linguistic system. is going to be in F. It will be a language for each agent. And we want to see how a state evolves in time. So I want to write down a dynamical system on the space of these states of the agents. So each Fi then is a map from X, which is taken to be in common for all the agents, to Y, also common. We can always expand X and Y to make it big enough to accommodate these agents. And I'm going to make one substantial hypothesis on the space of languages for the linguistic population. I want to assume convexity. Convexity needs a lot more discussion than I can give here, but roughly speaking, convexity has to do with the linguistic notion of creolization. How Creole was formed from languages English and French. Some kind of convex combination where one interprets the combination of two words as some sort of phonetic compromise or some choice of one word versus the other words. So Creole has words which come from the English, those which come from the French, and those which are somehow halfway between phonetically. Okay, but this is a serious hypothesis and important for our development. Okay. So now the idea is two levels. The dynamics of the space of states. This is the space of states will be Fk, if we want. Cartesian product of F with itself. K times, so it contains all these points. So we want a dynamics on this space. And it's going to be defined in two levels, as I indicated earlier. The superficial level via maximization of fitness, which will eventually involve maximization of communication. And on a deeper level, which does not use any fitness, but just uses learning theory, how agents learn a language from a given situation. And that's a much deeper thing. And with that deeper work on learning theory, we're able to recover the first situation. But the first situation, you can see the ideal dynamics laid out in front of you. So I'm going to do that. Okay, so I want to define a fitness function, phi I of F. And so it's going to be the fitness for agent I of some language F. That's the idea. All right. And this is going to involve some kind of social network in the linguistic community. This is something that's not present in any of the other models. Linguistic framework is given by a matrix, gamma ij. I and j running among the agents. And these are non-negative numbers. And they reflect the number of linguistic encounters between I and j. So if I and j never meet in any linguistic way, this will be 0. Okay. And so I call these non-symmetric effective linguistic encounters. So between then gamma ij, the encounters, number of encounters between agents I and j. And it's non-symmetric because the effect on the language is non-symmetric. For example, if I is a child, then the effect is very strong of a linguistic encounter with the mother, but not conversely. The mother's language is not affected significantly by encounter with the child. So an example of the matrix of a population of two individuals, mother-child, is the following. The mother is hardly affected, maybe say 0, affected by the child. And child's affected pretty big by the mother. Let me just write 1 minus epsilon. And I'll normalize this. And then I have to interpret the diagonal elements, gamma I. What does it mean to have a linguistic encounter with oneself? This is interpreted as inertia. That's consistent with this whole picture. So gamma I is very, very large, means that I is quite mature and has a strong tendency to stay with one's own language. For a baby, gamma I could be 0 or small. So here I'll put an epsilon, and here I'll put a 1. So this is an example of a linguistic matrix for population of two individuals, mother and child. Okay? As I say, be sure to check me if you have any questions. Okay. Another example is the following. We take islands on the opposite sides of the earth, say some Polynesian island versus Scotland. Then we'll have a matrix in here I could call gamma I, standing for Polynesia, and gamma 1, gamma 2, the zeros in here. Because there's no linguistic encounters between the two populations, you have this kind of a linguistic matrix. And I may comment at this point, we would certainly not expect these diverse islands to, linguistic islands to, over time, converge to a common language. So we can see here, no convergence to a common language. Okay. So now I want to promise to describe this fitness function. And so what I want to do is the following. This is fitness of a variable language for the ith agent given a certain state. So we're given a state F. Over here, we're given the languages of all the agents in society. Then the fitness, I suggest, could be defined with what I said in this way. We put gamma ij phi I of f equals this. So what this says, if f is close to language I, then, no, I'm sorry, this should be j here. It's close to j, then agent I, speaking f, will be able to communicate better with agent j. And this is weighted by the number of encounters that agent I has with j. So this is the weighting over linguistic encounters of the differences of a variable language to agent j's language. So if we put a minus here, this is fitness, and we want to maximize fitness over f. That will be motivated by the interpretation. Maximization here gives the language agent I with language f the best ability to communicate with the population that agent encounters. So we see this is going to give rise to the dynamics maximization of this function over. In this situation, it'd be very, very general, no hypotheses except convexity. Okay? So we want to solve this problem, maximize f. We want to maximize this function. And so the solution, this calculus of variations problem in this form, quite simple. the maximization star solution is given by the following equations. See, I have everything right there? I guess it looks okay. The minus sign is because we want to maximize function, maximizing fitness. So we write down the solution. It is f. Then we have sum gamma ij f minus f j. Just that. Those are the equations obtained by maximization.
I have a question.
Yes.
So that f is the multiple set of all the fi's?
What's that?
That f function?
Oh, I've used the f two ways, unfortunately, because the state, let me call f hat here for the state, all right? And so, yeah, so, is it okay?
So you're trying to find a function that maximizes it. Okay.
Yeah, right. Sorry, yeah. So this is the f here. This is just a variable f. I should say f belongs to f.
Thank you.
Okay, so you get this solution by easy calculus of variation argument. And you know, this you have to be careful. This is almost everywhere. But if we put in a little continuity, as we will eventually, then this is strictly true. Okay, so if we write this out, we get f equals sum gamma ij fj divided by sum gamma ij. All these sums over j. If I say j here, I should emphasize this sum is over j. I is the same here and here. Okay, so this is expressed simply by lambda ij fj. And now, something I learned a year ago, this lambda ij is a stochastic matrix. Lambda is stochastic. So I'm sure many of you know this much longer and better than I do. It means that lambda ij greater than or equals 0 is just a normalization of the gammas. And moreover, the sum lambda ij over j over the all elements in a row equals 1. Follows from the construction here. So it's a stochastic matrix. And now there is this beautiful theory of stochastic matrices that I learned about by reading undergraduate texts. And so we use that theory for analyzing the dynamics here. Now, that usually you can think of the stochastic matrix lambda as being a map from Rk into Rk. This is the traditional theory of stochastic matrices, but it goes over almost trivially to Fk and to Fk given by scalar multiplication. Because here we have to interpret, even at this stage, we have to interpret this. This is scalar multiplication of this number times this function. So that's what we have going over from Rk to Fk. So this is a linear operator on Fk. And eventually what one does is to analyze this in our Hilbert space construction, which we need for the individual behavior, we just use a spectral theory of this operator, which is not difficult to come by.
Excuse me, I got lost. So lambda ij is a stochastic matrix.
Yeah.
And this can be interpreted as a Markov chain.
Yeah.
The Markov chain is indexed by takes a value in the set of the adjuncts.
Yeah.
So you are going to describe an evolution in the set of the adjuncts.
Yes.
Well, in all the interesting cases, this kind of Markov chain never gets stuck in a single point.
Yeah.
They spread over all the adjuncts. So how can you interpret this result from a linguistic point of view?
Okay. Let me just say that if we take the language, say F star, the state, F star, take that state, okay? This is a common language. This is what I mean by a common language. Each agent speaking the same language. Okay, now we multiply this by a matrix lambda, and because the elements in a row sum to 1, this is a fixed point. So that's an example of a point which does not wander around. Under this operation, scalar multiplication, stochastic matrix times the state of function, the set of k functions. Okay? You can just check very easily the fact that all these, this condition here ensures that this is a fixed point of the matrix multiplication. Well, I shouldn't say matrix multiplication because we're on functions, but the induced map on the function space by stochastic matrix. Okay. So then the theory of stochastic matrices depends on some notion of irreducible. So we have irreducible lambda. Roughly speaking, irreducible just excludes this kind of situation. This is reducible. So let me not mention the exact notion of irreducible. It just means that there's a lot of enough linguistic encounters. So there's sufficient linguistic encounters so that one can't have this picture and a bit more. That's the notion of irreducible. And there's also a notion of primitive. Primitive means non-periodic. In our context, this is always assured because we reasonably assume that just some gamma I is not 0. If we assume that, then we get primitive. There's some agent with some inertia. So we make the standing hypothesis. So our theorem then is based on the theory of stochastic matrices, which says, let me just write this out then. T, the dynamics, T of F, this is the dynamics, is what I call it F hat maybe, equals lambda F hat. Where this is this operator I spoke of over here. This is the dynamics. And if I iterate, I get the powers of the matrix here. I get the kth iterates here. Okay? So understand the dynamics in our population model. We have to understand this object here. And lambda k, by this basic theorem, tends to, I can just say lambda k of v will tend to v star. V star, in the stochastic matrix setting, this will tend to, we have this tendency as k goes to infinity. For any v, we get convergence to a diagonal element. The picture is something like this. This is in this is in the classic setting. Here is Rk. Here's a point v, initial point. We start applying the stochastic matrix, and we converge to some point. It might be along a line like this, to an element of the diagonal. So this is assuming irreducible and primitive. You get convergence to the diagonal along some direction like this. Okay? This is now the theory of stochastic matrices. I apply the same thing to the same properties of lambda to the situation here, get the same conclusion. So that T, K, F hat converges to some common language. provided we have this irreducibility. Provided there is sufficient linguistic encounters between elements in the population. Obviously here, we do not get convergence to a common language because of lack of irreducibility. Okay? So this is pretty simple. This all goes from fitness maximization. No learning. But I think, yes?
You're assuming that lambda is independent of time.
Yes. Yes. That's right. There's many ways you can interpret that. You can interpret a child as a generic child, and eventually you can put an age of agents and so on. So lots of ways to interpret that to make reasonable sense. But I'm not saying it's the final word, because I want to get the simple things laid out in front of us, and then one can look to see if one can modify that to incorporate lots of legitimate questions. Okay, so we have this result. If there's sufficient linguistic encounters to make lambda irreducible, then we get the convergence of the language to a common language. And now we've seen over here how to interpret that. Here we have failure of irreducibility, and we have different languages in the limit. What about this example? This is not irreducible. Not irreducible. So this theorem does not apply. This is first main theorem, you can say. First main theorem, which gives a convergence to a common language. This is not irreducible, so the main theorem does not apply to the situation. But on the other hand, you would expect in this situation convergence to a common language, the language of the mother. So how to deal with that? Well, actually, one can strengthen this theorem a little bit by taking irreducible out and just say, use the Perron Frobenius, more detail. And so the one eigenvalue 1 should have multiplicity 1, and all the other eigenvalues, alpha I, are strictly less than 1, multiplicity 1. And that's sufficient to get the same conclusion. And so one uses a stronger theorem here, which is stronger than this, to incorporate this example too. Okay, so this gives us a picture of the Bear model. Now, let us put in, let's call this Fi. Now what I want to do is to expand this picture to individual learning, take out this hypothesis of maximizing utility, and have this same theorem obtained in the limit as the amount of conversation goes to infinity. So the idea is with just a finite amount of conversation exchanged, then one does not reach the limit, but one reaches a neighborhood of some limit. So that's more expressive of the actual linguistic community, where not everybody speaks the same language, but it's a neighborhood of the same language, so you have a common linguistic system, so people communicate well, even though it's not exactly the same, with a finite amount of conversation. And if you want the original theorem, you just take the number of examples, go to infinity. That's the idea. And so this uses the paper in the bulletin I mentioned. All right. So what we do is we take the same definition here, and now is a subtle point, but crucial. We just define Fi to be this quantity. Lambda ij have the same interpretation as before. We use the number of linguistic encounters in the same way. This network, social network, is the same. But now we interpret Fi at a given state as a filter for all the conversations that are occurring in the society. Fy will be interpreted as the examples which agent I hears, filtered through the number of agents that agent I encounters. So Fi represents the examples forwarded to agent I in this communication of speakers. The lambda I excludes, for example, lambda ij will be 0 for people that agent I doesn't meet linguistically. So that's excluded here. If they see that person a lot, it's incorporated into here. So this is an ideal language. Note here we've used convexity in this construction because, I should have emphasized one point. That where does the time? I should go back and say f hat goes into t of f hat exactly by sending f1 up to fk. Maybe you guessed this, into the f1 up to fk. This was utility maximization. So each agent chooses, so to speak, the language at the next time unit as obtained by maximizing fitness. So this is it's implicit in what I said, but let me write it down explicitly. This is the time of the dynamics. It goes via maximization. So now what we will do is say that this ideal language, this convex combination of the languages, this is the language that in one time unit, agent I is learning. So agent I is moving towards the language given by Fi. That's the way to reinterpret this, taking away fitness. This is the filter for example. So agent I is presented with a lot of conversation. In other words, presented with xi, yi, belonging to x cross y. These are meaning word pairs. For example, a baby might be presented with seeing a dog, then hearing the word dog by the mother. So in that case, here we have the meaning dog and then the word dog. So these are meaning word pairs, or more generally, conversation. These are the examples that each agent is presented with as filtered through this filter. Okay. And so now there is a theorem. Now let me state this theorem. This becomes a lot more technical. This theorem C star in the bulletin paper. And what it does is the following. We take this probabilistic measure on x cross y in such a way that the induced measure on x is rho x, as it should be, and the regression function associated with that measure is the corresponding Fi for agent I. Well, this is very brief now. Okay, so we want to measure this, F minus Fi squared. This would be the error in the theory of learning. So we want to know that this is small with large confidence. So actually, there's an integral in here. So we want to know that this is small. And now this will depend on the sample. In learning theory, what one learns depends very much on the sample. Sample can be very bad sample. So let me put the sample here, z. So z equals a set of xi, yi, 1 to m. The conversation, particular conversation up to some finite limit. So it's a sample. You could say m examples in that sample.
Excuse me, small f is what we call
Now, this here is a variable f. This is not f hat. Yeah, so the fi, see, each fi belongs to f. This is, yeah, so I'm working here FZ, I'm working for agent I here. So this is FZ belongs to F, not related to F hat so much. Strictly speaking, yeah, I could put in the M here, and it will depend on I also for agent I. Then I shouldn't call this I, but so this will depend on the ith agent, this too, and this will be an associated example, associated set of examples of conversation. And so one wants to estimate how close is what agent I is learning from that conversation. How close is that related to this ideal FI? That all the stuff, the language which is the filter. Okay, so this is estimated in terms of probability. It has to depend on Z. A bad choice here can make it a bad estimate. So this can only be estimated with a certain confidence. So we get that this probability over the particular samples is small. One is close to this language which maximizes communication. With confidence, 1 minus delta, then the crucial thing is to estimate this delta. And that's what we do much of the paper. This is given as a certain topological invariant. And now we have to put more of a Hilbert space structure on F. And here we would get some epsilon over a constant times Chebyshev-Bernstein number M epsilon over a constant. So this is the result, term C in our paper. So this allows us to make this estimate with some confidence. So the way the whole final theory goes is to use now the Hilbert space structures here on F. We have to impose now a Hilbert space structure, and a certain compactness is going to come in because of the covering number. So one uses something called a reproducing kernel Hilbert space. Or it could be a Sobolev space. And then a large part of our theory is to estimate these numbers, which we do. This is exponentially good, so this is a very good term here. Now the overall picture goes as follows. We take the ideal dynamics. Forget that it came from fitness, but we still have this ideal dynamics defined by lambda k. And now we take our space Fk and use a spectral decomposition of lambda on here. So now the set of fixed points is not just 1, so eigenvalue 1 will have a huge multiplicity. And we have, here's the diagonal in Fk, all the common languages along here. And now we'll take all the eigenvalues which are less than 1, take the corresponding eigenspace for that, maybe like this. And now we have to put on a new norm so that this becomes orthogonal to this. And in this new norm, one can show that this is a contraction. This dynamic, this pure dynamic is a uniform contraction onto the diagonal. So in the new norm, this looks more like this. So you're contracting onto the diagonal with good uniformity on the rate of contraction. Okay, once one has that, then one uses this theorem to approximate this pure dynamics with a learning dynamics. So for each set of samples Z, one gets a good approximation with good confidence, and the approximation improves more and more as this M goes to infinity. As M goes to infinity means the conversation goes to infinity. And so that way one gets a very quantitative version, because this is very quantitative, not asymptotic. One gets a very quantitative version of how one approaches an arbitrarily given neighborhood of the space of common languages. And one can see that in terms of all the ingredients of our linguistic system. Oh, yeah, I think I'll stop there. Thanks very much.
Any
Yeah, how do I define the law, the probability?
Yeah, how do you define it?
Okay. Yeah, so this requires some probability depending on the state. There will be a probability measure on x cross y such that the induced on x equals rho x, and then the regression function is fi. That gives a class. That doesn't say, it doesn't specify the probability distribution. It gives a large class of probability distributions with this property that gives on x the same as the space of frequencies on the space of meanings, and it induces fi as a regression function by, so to speak, integrating over the fiber, over y space. Is that okay?
Okay.
Okay. So here's x, y. Here's our samples. Now for x, what I want to do for this regression function is just to average all these, measure over the y space to get a point here. And I want that average to be f sub I.
Okay.
Yes.
You told that it's possible another model, or a more sophisticated model, if you use age and time from the language.
Yes.
The people, yes, that's what works about there.
Well, one does the same here, except one takes as the state, one puts fi, then we put in something like the age of I as part of the state. And then we have people dying off when they get so old and people being born, and you get more or less the same picture. And in fact, in that context, there is a big question here, a big paradox. Suppose we take that example of two islands, lambda 1, lambda 2, and instead of 0 here, suppose we put something small. Because, for example, England and France, you do have some kind of linguistic communication. But yet, we do not come to a common language. So this is a kind of a paradox of what I've said. And we have about half our paper will be solutions to this paradox in different ways. And I've indicated one already, but one has to go much deeper and look at things like effects of a previous culture. And that's related a little bit to this age-dependent model. You have to put in some kind of immortal agents like Shakespeare to explain how you can still have irreducible lambda and keep different languages. Yeah.
So I have a slightly different question about modeling. I think it perhaps is taken care of by an expansion of your white to black continuum, and that is that a symbol can have ambiguous meanings. That is, this furry
Sure.
object can be a dog, it's also a Labrador, it's also a carnivore.
Yeah.
It may have a number of different meanings in different contexts.
Yes.
Is that taken care of by this idea, this mapping into a number of acts?
Yeah, I mean, you can put in here, different kinds of dogs at the corners of a simplex here, and then the language could illustrate the likelihood this is one kind of dog versus another.
Yeah, or whether the meaning of this thing is dog or species or animal.
Yeah, right. That's right. So in principle, I think one can do all these things. To actually do it is, it's not.
But the point is, it's not a question of doing it for examples, but the idea that your notion of a mapping takes care of this.
Yeah, that's right. But on the other hand, I'm not wedded to the idea that it should be a mapping. I could see some kind of version of this model where you take words and meanings treated more symmetrically. I could see that. But it would take technically more work. And for the basic model, I think it's not necessary.
Any further questions? For tomorrow,
My name is Antonio Galvez. We're very